Okay, let's jump right into this explainer. Today, we're demystifying the absolutely mind-bending reality behind modern AI image generators. You've probably messed around with them yourself, right? You type in a few words, hit enter, and watch a masterpiece magically appear on your screen. But the underlying mechanics of how they actually pull this off are usually hidden under a shroud of mystery, kind of treated like some sort of computational magic. Well, today we're popping the hood. We're going to explore the stunning intersection of machine learning and physics that makes literally all of this possible.
Think about this for a second. It's truly a marvel to realize that an AI can conjure a completely unique image, say a never-before-seen red panda, out of pure randomized static. I mean, there is nowhere on the internet where you can find that exact combination of pixels. It's a brand new creation, pulled right out of thin air. How exactly does a system look at television static, which contains absolutely zero visual concepts or information, and decide to slowly mold it into a hyper-realistic animal, a sprawling landscape, or a futuristic city?
As wild as it sounds, the secret to generating these uncanny images isn't just computer science. It's actually deeply rooted in non-equilibrium thermodynamics, the physics of ink dispersing in water. Back in 2015, researchers made a totally unexpected connection. The exact same mathematical framework that physicists use to study how smoke disperses in the air is what led to those early, bizarre AI videos of a fake Will Smith eating fake spaghetti. And eventually, that exact same math evolved into the hyper-convincing generative AI we use today.
Which brings us to Section 1, the vast space of images.
To really grasp how this works, we need to completely change how we think about a picture. We have to zoom out and visualize the unimaginable space where all possible images exist. Let's think of data not as a flat canvas, but as a vast, sprawling landscape shaped by probability. If you take a standard 1000 by 1000 pixel image, you are instantly dealing with a staggering 1 million dimensional space. Every single pixel represents a unique axis, a unique dimension, and every pixel holds a value between 0 and 255. Can you even picture a space with a million directions? Any image you have ever seen, or could ever possibly see, exists as a single highly specific coordinate inside this bounded million-dimensional reality.
Now, in this impossibly vast map, this million-dimensional hypercube, most of the terrain is completely empty, chaotic static. It's just a massive flat valley of zero probability. Real images, on the other hand, form tightly knit, isolated clusters. So a picture of a banana belongs to a very specific tiny cluster coordinates. A picture of a cat playing a piano is in another isolated cluster, far, far away. These clusters are like little hills of meaning, completely surrounded by an endless ocean of absolute visual noise. Finding a real image in here, it's like finding a microscopic needle in a cosmic haystack, because a good image has to follow highly specific rules about how neighboring pixels relate to each other.
Moving on to Section 2, the physics of chaos.
So the crucial question is, how does a computer navigate this million-dimensional void to find those incredibly rare clusters of beautiful images? If the landscape is almost entirely meaningless static, dropping a random point into the space means you're almost certainly landing in the middle of nowhere. How do you find your way back to a hill of meaning? Well, instead of trying to rigidly map out the entire landscape like traditional machine learning, diffusion models act as a localized compass. Think about it this way. Trying to memorize the entire million-dimensional landscape from your training data is like trying to memorize every single street in New York City. That might work for New York, but it's totally useless if you get dropped into San Francisco. Diffusion models don't build a static map, they build a compass. When placed in any random, noisy location, this compass just tells the system which local direction to step in to find slightly higher probability, gradually revealing the structure of the world around it.
And this brilliantly illustrates how AI borrows from a rich history of physics, tracking the chaotic, jittery motion of particles over time. Actually, this isn't just a loose metaphor. Back in 1827, Robert Brown observed the chaotic motion of pollen in water. By 1905, Einstein quantified this spreading phenomenon. Later, Norbert Wiener modeled it mathematically, and then in 1982, Brian Anderson proved that this diffusion process is mathematically reversible. It's absolutely amazing to think that watching pollen float in a glass of water in 1827 is the direct mathematical ancestor to the AI art on your computer today. We're literally taking centuries of physical science and applying it directly to digital pixels.
We use these physics concepts for what we call forward diffusion. It acts just like ink dropping in water to deliberately destroy a perfect image by adding noise until it's entirely lost in the valley of chaos. We start with a pristine image from our dataset, and step by step we inject Gaussian noise. We are taking that coordinate right off its structured hill and shoving it out into the flat, empty wasteland of static. It sounds totally counterintuitive to intentionally destroy a perfect image, doesn't it? Why ruin perfectly good data?
but this is exactly how we set up the environment for the model to learn.
Let's look at Section 3, Training and Navigational Compass.
Okay, so we've pushed our image out into the noisy void. Now, how do we build that compass I mentioned earlier to find our way back? Well, unlike traditional classifiers that just spit out a tiny little word like cat, a diffusion model outputs a massive vector direction, all without needing a single human label. This is a huge paradigm shift. If you want a traditional AI to recognize cats, humans have to manually tag thousands of cat photos. But with diffusion, the output is exactly the same massive size as the input. It hands you a 1 million dimensional instruction manual on how to change every single pixel. And because we're generating the noisy images ourselves automatically, the supervised learning pairs are entirely free. Zero human labeling required. This right here is the secret cheat code that made training these massive models actually possible.
We train this compass automatically by adding noise to a good image and then making the model predict that exact noise. This way it learns the precise gradient to step back towards structure. Geometrically, that noise sample we added acts as an arrow pointing away from the cluster of good images. So we show the network the noisy image and ask it, hey, what arrow brought you here? We add the noise, and then we ask the model, how did we get here? If it learns the path out, it inherently learns the path back in. Once the model can predict the arrow that dragged it out into the noise, it can just reverse that exact arrow to step right back toward the clean image.
You can basically think of the model as a blindfolded hiker in a foreign landscape, simply feeling around with their feet to find the steepest descent back up the hill of probability. The hiker has no map, they have no idea where the top of the mountain is, but by feeling the ground right beneath their boots, they can take one small step up the incline. Then they feel the ground again, and take another step. This is gradient ascent in a probability landscape.
Finally, Section 4, Journey Back to Reality.
We have our trained compass. Now it's time to let it work its magic during the inference, or sampling phase, to generate brand new art from scratch. To create an image, we drop our model into a totally random location of static, and we take iterative steps using our compass until we land safely inside a cluster of meaningful pixels. We start in the dead center of the noisy wasteland. We ask our trained compass for a local direction, take a tiny step towards structure, and then ask again. We have to do this iteratively in lots of small steps, because if we took one massive leap based on the very first reading, we'd overshoot entirely and probably end up right back out in that flat, empty wasteland.
And if you're wondering how it decides to draw a cat instead of a house, it's just pure chance. The initial random static simply landed a tiny bit closer to the cat cluster than anything else. There is no hidden catness secretly embedded in the TV static. The noise contains zero visual information. It's simply that, in this million-dimensional landscape, the spot where we randomly dropped our hiker happened to have a slope that eventually led up a hill made of cat images, rather than a hill made of banana images or toaster ovens.
Now, to speed this epic journey up, modern AI often swaps jittery, stochastic, mathematical paths for smooth, deterministic ones, which slices generation time down massively. The original math, using stochastic differential equations, or SDEs, injects noise at every infinitesimal step, making the path incredibly jittery. It required 1,000 tiny, careful steps just to get a good result. But researchers realized they could use ordinary differential equations, or ODEs, which drop that random jitter entirely. This smooths out the path, allowing the models to take much larger, confident strides, cutting the required steps down to just a few dozen. This mathematical shortcut is the literal difference between you waiting 5 minutes for an image or getting it instantly.
All of this leaves us with a fascinating takeaway. The magic of AI generation is really just mastering the physics of navigating back home from the void. Generating beautiful art is essentially performing gradient ascent on a probability distribution derived straight from thermodynamic principles, which really makes you wonder, if we can build a compass to navigate the million-dimensional space of all possible images, what happens when we point that exact same compass at the uncharted landscapes of our DNA, or the fundamental structure of reality itself?